Dear audience, welcome. Sparse training such as DeepR, ICT, RAGO, and DSR that maintains sparsity throughout the whole training phase shows great potential towards end-to-end neural network training on the edge device. They share the similar training method that maintains sparsity level during the entire training phase, while altering network topology to explore better training performance. Sparse training starts with a sparse model picked intuitively from the initialized dense model, and then heuristically explore various sparse topologies with the given sparsity ratio while training the model weights. Specifically, the topology exploration is done by altering the network connection in the manner of network pruning and growing. The underlying principle of sparse training is that the total epoch number is the same as dense training, but the speed of each training iteration is significantly benefited from sparse due to the reduced computation. In the previous approaches, the unstructured sparsity is studied. However, challenges exist in the sparse training domains, both in training algorithm level and the acceleration level. In algorithm level, previous work used simple protocols that change network topology while achieving limited training results. Additionally, previous work used heuristics that involved full-size matrix computation. For example, in order to determine the desired pruned weight at initialization, several works use a few iterations of dense forward and backward computation, which is still computation and memory intensive and is therefore not compatible with the end-to-end sparse training on the edge device. On the other hand, when networks are initialized as a sparse network, the pruning and growing involves computation of all gradients corresponding to both pruned and non-zero weights, and therefore their memory footprint is equivalent to dense training. In acceleration level, we all know that DNN always prefer to involve complex and intensive computations in order to ensure good performance. However, heavy computation burden makes it impossible to train a neural network on a resource-limited device. The use of sparsity in training is intended to solve such problem. However, current methods prefer to use unstructured sparsity scheme to demonstrate theoretical computations reduction in training, while fails to recognize the fact that unstructured sparsity has plenty of problems in actual implementation. The irregular weight distribution brings many problems, such as poor data locality, load balance issue, thread divergence, and complex control flow instruction. We propose memory-bounded sparse training with the elastic commutation. The main idea here is to altering the less important non-zero weights with zero weights to explore more sparse topologies with the specified sparsity schema and ratio without increasing the memory footprint during the sparse training process. The above figure shows MBST with elastic commutation. The box is representing a neural network. The number in the box is the sparsity ratio. Red box indicating pruning operation, and the green box is indicating growing operation. During training, the model are initialized with random sparse mask with a target sparsity ratio. We mutate network topology at every few training epochs by pruning unimportant weights and randomly growing back connections to restore target sparsity ratio. We separate the training phase into several subphases by several milestone epochs. We call it elastic mutation because we decay the pruning sparsity ratio at those sub-training phase. During the entire training process, the model sparsity is strictly bounded by target sparsity ratio, thus maintaining a hard memory bound. In addition, the mutation process is actually operated on indices to facilitate implementation on the edge device. If the memory footprint could be a soft constraint, we propose an enhancement with the soft memory bound and SMBST with elastic mutation as an option to further improve accuracy. In SMBST, the mutation process is as follows. First, grow the model to reduce the sparsity ratio, then remove weights to increase the sparsity ratio back to target sparsity ratio. Models are slightly denser during the majority training phase. Note that even with a soft memory bound, the target sparsity ratio can still be met by the end of the sparse training. By introducing more zero weights in sparse training, we ease the SGD process with a smoother training loss surface. Thus, we can achieve better accuracy. In our implementation for training acceleration, we adopt the pattern-based sparsity along with the compiler optimization on mobile phone. The pattern-based sparsity is a kind of fine-grained structure sparsity which can achieve both high accuracy and hardware friendliness. It is a better sparsity solution which can reduce thread level divergence. This figure shows our proposed compiler assistant scDNN sparse training framework. The key step in the compiler optimization is the filter kernel reorder. When a pattern-based model is trained, patterns and the connections of all kernels are already known, which means all computation patterns are fixed. We organize the filter with similar kernels together to improve inter-thread parallelism, and then order the same kernel in a filter together to improve the intra-thread parallelism, just as the figure shows. In this way, some patterns can be executed in the same time, which eliminated all the execution branches, thereby higher instruction level parallelism. And the similar filter can also be executed by the all thread simultaneously to minimize thread divergence and load imbalance. The compiler level optimization principle fit both forward and backward propagation. In this way, we can actually achieve training acceleration on resource limited devices. In this slide, we show the accuracy results of the proposed memory bounded sparse training and the soft memory bounded sparse training algorithm. We first use unstructured sparsity in our evaluation on both CIFAR and ImageNet dataset. Compared to other work, our CIFAR 10 and CIFAR 100 result on recent 32 outperform other baselines, including the most recent state of the art. On ImageNet evaluation, we test our proposed sparse training algorithm, and we found that we can outperform state-of-the-art baseline using less training effort. In 80% total sparsity, the accuracy can even surpass the pre-trained dense model accuracy. In this slide, we show the accuracy and hardware performance of the pattern-based sparsity scheme along with the other sparsity scheme in sparse training. Figure A and B shows the accuracy results of different sparsity scheme on Reson 32 using MBST and SMBST respectively, and compared with the state-of-the-art works. Besides channel pruning, for most of the sparsity scheme in various sparsity level, MBST and SMBST achieved comparable or higher accuracy than other reference work with unstructured sparsity. Figure C shows the comparison with the representative state-of-the-art works in accuracy, training acceleration rate, and memory footprint using Reson 32 or CIFAR 100. Sparsity ratio is 90% for all results. The acceleration rate is normalized with respect to dense training. The size of the circle represents the relative cost of memory footprint. All unstructured sparsity results only achieve minor training acceleration, which is 1.4 to 1.27 times, because the unstructured sparsity lead to irregular memory access, which introduce significant execution overhead. For our pattern-based sparsity scheme, the acceleration rate are greatly increased and achieved up to 2.3 times acceleration compared to the dense training while maintaining comparable accuracy. From the memory footprint perspective, SNP and GRASP involves dense model training during at initialization. Their memory footprint are considered the same as the dense model. Because fewer indexes are needed, the pattern-based sparsity have smaller memory footprint than unstructured sparsity scheme. Overall, our result shows a clear advantage compared to the other reference work, and both of our MBST and SMBST memory achieve the Pareto optimal in all accuracy, training acceleration, and memory footprint perspective. Thank you very much.